Okay. Okay, organic chemistry 2. We're getting into activating groups today. You know, earlier we talked about nitration, and we talked about the nitration of benzene, and we said, okay, well, you have to combine nitric acid and sulfuric acid together. We even went over the mechanism. We say, well, the sulfuric acid is a much stronger acid than nitric acid. Therefore, it's going to protonate it, and water leaves, and you make this thing called a nitronium ion. So just to refresh your memory, you make this really electrophilic species called a nitronium ion. Let's pencil it in here. So here it is, and of course that is made in situ, meaning it's made by combining these reagents. Now we talked about nitration of benzene, but what about toluene? This is toluene. And when we're thinking about toluene with respect to benzene, there's two questions that we can ask ourselves. Number one is, what is the effect of the methyl group on the rate of the reaction? You know, if we have this methyl group here, is it faster? Is it slower? And it says here that actually toluene reacts a lot faster than benzene. That's pretty neat. Well, the reason why is that a methyl group is electron donating, right? A methyl is an electron donating group. Now, if you can't remember why, it's based off of something called hyperconjugation. And we have this electron donating group that donates electrons towards the ring. Therefore, it's going to make it a stronger nucleophile, right? The electrons that are in the ring are even more available because there's electron density being poured into that ring, if you will. So number one, it's faster. And then number two is like, okay, well, I have a methyl group on my ring. Where is the nitro group going to go? Is it going to go in the ortho position? Would it go in the meta position? Or would it go in the para position? Where's it going? So what we're asking here is, what's the regioselectivity of this reaction? There's three possible products, aren't there? I could add it in the ortho position, the yellow carbons. I could add it in the meta position, the red carbons. And I could put it in the para position where the blue carbon is. So what do we get? Well, let's take a look. If you actually try this reaction, so here's the reaction. Somebody's done it. Good thing. Somebody took toluene and they treated it with nitric acid, sulfuric acid. They made the nitronium ion, and they found out that they got three products. They got the ortho, the meta, and the para. But what you probably noticed right away is that there's very little meta formed, only 3%. That's next to nothing. That means if you got 100 grams of product, only 3 grams of it would be the meta nitrotoluene. So very little of that, but we get a substantial amount of both the ortho and the para. Well, why is that? And this being organic chemistry, we're going to provide a rationale for that, and it's tied to the mechanism. So let's take a look at the mechanism of nitration. And what we're going to do is we are going to compare the relative stability of the different sigma complexes that we make, depending on whether we have ortho, meta, or para attack. Check this out. If you do ortho attack and we look at the sigma complexes that are formed, okay, all three of these here, well, you probably noticed that one of them is highlighted in a green box. Why is that? It's because there's an inherent stability in this sigma complex that isn't present in these two right here. What is it? Well, it's the fact that you have a positive charge right here adjacent to an electron donating group. And so what's happening is that this sigma complex, this particular contributor to the resonance hybrid, is more stable than the other two. Why? Because you've got electron density from our electron donating group being poured into that positive charge. And what does it do? It stabilizes it. Okay, we see that with ortho attack, and we also see that when we draw the mechanism of para attack, and we compare all three contributors to the sigma complex, and we look at the one that's highlighted in green, and we see that we have a positive charge on this carbon, which is adjacent to the methyl group, which is pouring electron density into it, and therefore stabilizing that. Now, both of those resonance contributors that we see in those green boxes, you don't see it anywhere in here. Take a look. If you look at the resonance contributors for the sigma complex of meta attack, what do we see? We have a positive charge down here, over here, and over here. None of them end up on the carbon that is adjacent to the methyl group. And so none of them have that extra stability that we see when the molecule undergoes either ortho or para attack. Now that is what a big chunk of the first few minutes of this lecture are going to be based on. Give me a thumbs up if you follow me on that. Is everybody with me on just the rationale? Those two resonance structures in green are more stable than anything else on this page. Cool. Yeah. Well, again, you know that table that I showed you before we even started the lecture today, table 18.1, and I said don't be intimidated? Well, here's the reason why. If you understand why these resonance contributors are more stable than everything else, and that is the rationale for why we get more ortho than para, or sorry, why we get more ortho and para product than we do methyl, then you're not going to have a difficult time understanding when we see meta substitution as the major product. Well, let's take a look at the reaction coordinate diagram for the formation of all of these sigma complex, whether it's from ortho, meta, or para attack. Now you notice the activation energy. I'm just going to pencil it in for the ortho. So we have our starting material, we have our activation energy shown here, and you notice that the activation energy for the ortho attack and the para attack are significantly lower than that for the meta attack, right? The one for meta is much higher. And what do we know? Well, if the activation energy is lower, it means the reaction is faster. And so we're going to get these reactions occurring more so than the meta attack. And that is why the ortho and para predominate. But there's something else kind of curious about this slide. Did you notice, and maybe you did, maybe you didn't, if you look at the height of the activation energy for ortho attack, and you compare it to the height of the activation energy for the para attack, the way they put it on the slide is that the activation energy for the ortho attack is actually slightly higher, but we make more of it. Well, why the heck would that be? Why would you end up with more of the ortho if its activation energy is slightly higher? Well, I bet you if I gave you a couple seconds to think about it, I'm sure that everybody here could come up with some kind of rationale. And I bet you that it would have something to do with, well, Mr. Dion, there's two ortho positions, right? There's two of those, but there's only one para position. And so just based on statistics, statistically, we should get about twice as much ortho as we do para, and we see that it's not exactly twice as much, but we end up with significantly more of the ortho product than we do the para product. So more ortho is formed because there's more ortho positions. Now hold the phone before you think you can hitch your wagon to that for every single example. Well, unfortunately, it's not always the case. This rationale that's shown at the bottom of this slide, I'll just be totally frank with you, this is kind of an exception, actually. We don't see this for a lot of other compounds. It's really only toluene that you see this for. We'll even write it down here, mostly with toluene. And the reason why is just because the methyl group is so small. And what you're going to see is if you have a bigger substituent, it might not necessarily work out that way. So why don't we take a look at an example where we have one substituent that can donate electron density, but something that's even bigger than a methyl group, and something that can donate even more electron density. So let's turn our attention to anisole. If you remember anisole, so anisole was a character on Friends. No, I'm kidding. That's Jennifer Aniston. Anyhow, anisole is this compound here, methoxybenzene. And if you try the nitration on anisole, you actually find out that it's 400 times more reactive than toluene. Now, why the heck would that be? Well, check it out. If you take a look at the structure of anisole, if we just zoom in here on the structure of anisole, I mean, what's something that everybody has memorized? The electronegativity of oxygen. Everybody that's hearing the sound of my voice knows, or at least should know, that fluorine is the most electronegative element. It gets the gold medal, but silver, the second place in the periodic table, goes to oxygen. Oxygen is a really electronegative element. And so based on induction, it is withdrawing electron density away. So you might say, hey, well, hold on, a methoxy, that's electron withdrawing. Therefore, that's going to make the aromatic ring a really weak nucleophile, but that rationale would be incorrect. Why? Because not only do we think about, or do we have to consider the fact that the oxygen is inductive and can withdraw electron density through induction, it actually donates electron density via resonance. Check it out. You can see all four of these resonance contributors down here, I mean 5 total if you count or actually, sorry, there's only 3 that are shown here. But anyhow, we have anisole, and then we have 3 additional resonance structures that we can draw here for the resonance hybrid. And what do you notice? That because of resonance, it dumps a lot of electron density in the ring. You could not draw a resonance contributor for toluene where you show a negative charge in a ring. I'm sorry, but you can't do that. But here you can. So what does that tell you? That tells you that this thing can donate a lot of electron density, which renders the ring more nucleophilic. Now, there is a little aside in our textbook where he says, okay, well, if it ever comes down to, kind of a battle where you're trying to decide, well, what's going to have the stronger effect? Will it be induction or will it be resonance? When it comes to activating and deactivating groups, resonance is always going to come out on top. And so we basically come to the conclusion that anisole is a stronger electron donator because of the methoxy group, and it's going to be even more reactive than, much more reactive than toluene. Now check this out. Check this reaction out. You're going to think this is pretty neat. And this is a reaction you kind of have to memorize. So I'm going to write that on here just so you're fully aware. Memorize this reaction. Now, I'm not telling you to just blindly memorize it, like just know it, you guys, okay? I'm going to explain it, but it is kind of an interesting thing that we look at, today, and it can come up in the practice problems. It can come up in the homework. So check this out. You remember we said, like, if you go back to a couple of days ago, I said, okay, you guys, if you want to do a halogenation on benzene, right? I said, look, if you take bromine and just try that, you get nothing, no reaction, right? I said, you've got to spruce the reaction up with some iron tribromide or iron 3 bromide, which creates a really powerful bromine electrophile. And then you can do the bromination, right? I said, you'd add a bromine. Well, because that methoxy group is so activating, you don't need any Lewis acid. So no Lewis acid required. If you just take that anisole and treat it with just plain old bromine in excess, it brominates in both ortho positions and the para position. So you end up with, it would be a 2,4,6 tribromo anisole. So it just poly substitutes, and it's actually difficult to avoid that. However, are you ready for this? In our class for Chemistry 3111, okay, for Chem 3111, we're always going to assume that you get monobromination and that it always occurs in the para position. So for our class, what we're going to assume is this. If you take anisole, right, so if you take some anisole and you treat that with bromine, Br2, it's just going to brominate in the para position. Right down there. Okay, now there's something else that you might be wondering. Well, Mr. Dion, I thought you said, if you had toluene, you got more ortho than para because, statistically there's more ortho positions than para positions. So why would we assume that it goes at the para position? Well, I told you that with toluene, it's actually kind of an exception. Usually compounds will preferentially do their substitutions at the para position, and you can guess why. It's because a methoxy is so much bigger than a methyl group that it actually partially blocks the ortho positions because this is so dang big, and we know we have free rotation around this bond. And so it preferentially substitutes at the para position. And so that's the rationale for that. And that is mentioned in the book, of course. I didn't just come up with that on my own. Anyhow, so let's take a look here. It says, like the methyl group, the methoxy in anisole is activating, and it's an ortho-para director. And here it's showing exactly what I just told you, that, we have an electron donating group, just like we did with toluene. So we see very little meta, 2%, it's next to nothing, but we see a whole bunch of ortho and para. Now, in this case, it's different than toluene. We get a bunch of para, mostly para, and a little bit of ortho. And again, the rationale as to why we get less ortho, because, with toluene, we said, well, come on, statistically, there's 2 ortho positions. The reason why you get less ortho is just because the methoxy group is so big and it causes steric hindrance at the 2 ortho positions. So that's the rationale. And those are both, kind of things that you need to just be aware of. Again, why is toluene an exception? It's because just a little old methyl group is so small. But usually, most other activators that we see are going to be big enough that we preferentially are going to do our substitution at the para position versus the ortho position. Now let's take a look at the sigma complexes when we do the ortho, meta, or para attack on anisole. So here we have all of our sigma complexes, and you notice the difference between the ortho and para attack, what they've got that the meta attack doesn't have. And what is it? They both have one extra resonance contributor that isn't even present in the sigma complex that results from the meta attack. Check it out. Let's just take a look at ortho. Okay, so here's our nucleophilic attack, the first step for all of these. So we have our nucleophilic attack, and here's our sigma complex. We have the positive charge here, so maybe I'll use my highlighter. Skips a carbon, then it's down here, then it's up here. But look, if you look at this resonance contributor right here, instead of drawing this arrow, they could have just as well done this, right? They could have poured the electron density into that empty p orbital to make a new pi bond and end up with this resonance contributor right here. And there we go. So we end up with an extra resonance contributor. We end up with the same thing when we do the para attack. But look, when you do the meta attack, you end up with no such thing. There is no sigma complex where you have a positive charge adjacent to the oxygen. And since the sigma complex is less stable, you get less meta attack. Give me a thumbs up if you follow me on that one. Another concept that's really important. And again, if there's any question, don't hesitate to stop me. That's what I'm here for. Never hesitate to stop me and interrupt me. But I'm glad you gave me the thumbs up on that. And, let's take a look at the reaction coordinate diagrams. And what you're going to see is something very similar to what we saw with nitration of toluene. Check it out. The activation energy for the ortho attack. So here's our activation energy for the ortho attack, and the para attack is much smaller than that of our meta attack. Look at this thing. This is a giant activation energy. So high. The reaction's going to be slower. Rate's going to be slowed down. We're going to end up with less nitration at the meta position. And you notice that the activation energy for the para attack is smaller or lower, excuse me, than that for the ortho attack. Well, why would that be? Again, it's partially due to the fact that you have free rotation around this sigma bond, and it causes some steric hindrance at the ortho positions when we have that big old methoxy group. So there you go, activating groups. And what did we see? What did the methyl group in toluene and the methoxy group in anisole? If we just take a look at those two compounds, we had toluene. We said that was 25 more times reactive towards nitration than benzene. And then if you had anisole, we said that was 400 times more reactive than toluene. Why is it? Because both of them possess electron donating groups, right? Activating groups are going to be electron donating groups, EDGs. And therefore, I'm sure that you can imagine if we have a deactivating group, I bet you can guess what it is. It's an electron withdrawing group, and you would be 100% correct. What's an example of a very strong electron withdrawing group? The thing that would pop into my mind most of the time would be a nitro group. If you have a nitro, so RNO2, and you need to know how to draw that Lewis structure, so we have R, we have a zwitterion, because we have a negative charge on the oxygen and a positive charge on the nitrogen. All right, so here's the Lewis structure of our nitro. Here it is. This is nitrobenzene. Again, what you're seeing here in this full-on Lewis structure is the same thing as this, okay, just NO2. All right, but it says here the nitro group is deactivating. Why is that? Because it's inductively electron withdrawing. Well, why would that be? Because nitrogen has an electronegativity of 3.0 and carbon is only 2.5, and therefore you're going to have a dipole going towards the nitrogen. But check this out. You can also draw resonance structures where you delocalize the negative charge onto an oxygen of the nitro group. Look at this. You could pour electron density out like this. Now, I'm going to erase those arrows because they should be shown down here, and that's exactly what you see right here. You see that if you draw the resonance contributors to the overall resonance hybrid of nitrobenzene, check this out. You end up with 3 resonance contributors where it actually shows a positive charge in the ring. Keep in mind, these aren't sigma complexes, right? This has got nothing to do with a sigma complex. There's been no nucleophilic attack. We're just looking at the resonance structures of this compound. I could have asked you this in chapter 2 of Organic Chemistry 1. What's your point, Mr. Dion? My point is this. If we can draw resonance contributors that literally shows positive charge in the ring, it's positively charged, man. How much do you think it's going to want to give away electron density? How nucleophilic do you think this thing is going to be? How much does it want to do that? It totally can if you hit it hard enough. But does it want to do that? No, because this thing is sucking electron density away like crazy. And that is why a nitro group is so deactivating. Check this out. If you want to nitrate nitrobenzene, it says nitrobenzene undergoes nitration 100,000 times slower than benzene. Now, when we were talking about activating groups, we were talking about 25 times, 400 times. Now we're talking about 100,000 times. That tells you this thing is just crazy deactivated. This thing's like, no, it's like, George Bush Sr., he's like, don't want to do it. No, not going to do it, right? Doesn't want to react. And that's why you got to jack the temperature up. When was the last time anybody ever asked you in a lab, like, hey, could you crank this nitric and sulfuric acid up to 100 degrees? Something I wouldn't ask an undergraduate to do. Doesn't sound like something I would want to do every day anyway. You're boiling or refluxing some of the strongest acids that we look at in this class. That's what it takes to reach the necessary activation energy levels in order to get the nitration to occur. And look at what we get for products. We actually get almost all meta. Okay, almost completely meta. You get next to no para, and the ortho is pretty pitiful too. Very little of both of those. Now, if you're wondering, like, why would that be? Well, you can imagine that the answer is hidden, or not hidden, but the answer can be uncovered, so to speak, by looking at the mechanism and studying your friend and mine, the sigma complexes. Everybody's favorite, right? I'm sure you're sick of sigma complexes by now, but they're pretty rad. Now check this out. If you look at the ortho and para attack, you notice that both of them have 2 resonance structures in the sigma complex that are highlighted in green. Now, what's so special about those? What it's trying to tell you is that these are really unstable. Okay, so very, very, or maybe not very unstable. We'll put here very high energy, super high energy. Right, so it means it takes a lot of activation energy to put the nitro group in this position. Well, why would that be? If this is electron donating, if this is electron withdrawing, how badly do you think a molecule wants to have something that's electron withdrawing and then put a positive charge, just plunk it right next to it? Now, does that look energetically favorable to you? It certainly doesn't to me. If you have a positive charge, what do you want to do to stabilize it? Opposites attract. You would want to pour electron density, but a nitro group is electron withdrawing, so you get this thing sucking electron density away. Then you've got a positive charge right next to it. I mean, what the heck? That is very high energy, and therefore the activation energy to make this sigma complex is super high. We see the same thing with para attack. We can draw the same resonance contributor where we have that strong electron withdrawing group adjacent to a positive charge. That is not good. No. But if you look at the resonance contributors to the sigma complex for meta attack, look at these. Look at all 3 of them. You have the positive charge here, positive charge here, and positive charge here. You never end up with the positive charge on the carbon next to the nitro group. Doesn't happen. And since that doesn't happen, that means that, hey, this might not be easy to do. It might have a very high activation energy. It might be unreactive, but if you get the reaction to go, if you do provide it with enough energy so that it can cross that activation energy barrier, well, it's preferentially going to go in the meta position. Why? Because the activation energy to get the meta attack to occur is actually lower than that for the para and the ortho. And again, it's all based on what? The sigma complex. So that's why if you're wondering, why did he spend so much time talking about sigma complexes last lecture? Why was that? Why did we look at the sigma complex for every dang thing that we talked about? Sulfonation, nitration, Friedel-Crafts alkylation, acylation, bromination, chlorination. The reason why we did that is because it's so crucial that you understand sigma complex in order to understand what an what an activating group does and a deactivating group. Is everybody with me on that? Any thumbs ups for that? Just the kind of the rationale of why a deactivating group behaves the way it does. All right. Now, before we can get into looking at that table and trying some problems, which we're going to do, I promise, we're going to try some problems in a few minutes. But are you ready for this? And I'm sure you all read the textbook before coming to class. You're all great students. In fact, I'm 99.9% sure my students always read the book before coming to class. But we're going to have to look at an exception. So somebody asked a question in the chat, is there any process you could use to just get a specific unfavored product? Yes, there are some processes we can use, Nick. We can use what's called a blocking group, and we're actually going to cover that today. So let's say you have, let me just give you an example since this is in your brain at the moment. All right, Nick, let's imagine you had cumene. Do you remember this molecule? Not drawn with a highlighter, but this one here. Cumene, which is isopropyl benzene. If you take this compound and let's say you wanted to put a bromine in the ortho position, well, you can imagine that isopropyl is so dang big that if you try to brominate that, everything is going to go in the para position. And so there's a technique that we can use using what's called a blocking group that will enable us to put a bromine on the ortho carbon. Does that help? We will address that. Not every possible example on God's green earth, but we'll look at a specific example. Yeah, and it's very cool. Very, very cool chemistry. Okay, so here's the exception that we have to look at before we can summarize activating groups, deactivating groups. What's an ortho-para director? What's a meta-director? Well, there is an exception, and that is the halogens. Now, we're not really worried about fluorine a whole lot in this chapter. When we're talking about the halogens in chapter 18, we're talking about chlorine, bromine, and iodine. And the reason we don't talk about fluorine really, I'll get into that more later on in the course. But it says here that all electron donating groups are ortho-para directors. Cool. All electron withdrawing groups, like a nitro, are meta-directors, except the halogens. Oh boy. So it turns out that the halogens actually withdraw electron density by induction, right? So they are deactivating. You think about chlorine, bromine, they have high electronegativities. I mean, chlorine has an electronegativity of around 3, bromine is around 2.8. And so if you put, let's say you put let's put a chlorine. Let's say you have chlorobenzene. Well, this chlorine can pull electron density away from the ring. So you think, okay, it's a deactivator. There you go, meta-director, done. Well, in fact, even though chlorine and bromine and iodine are deactivators, it turns out that they actually activate, if you will, or they donate electrons through resonance to the ortho-para substituents. And so they're preferentially going to do electrophilic aromatic substitution at the ortho positions and the para position. Now, if you're wondering, why the heck is that? Oh man, this is so annoying, Why would that be? Well, I bet you can guess what it's based on. It's based on the sigma complex. So this slide is just summarizing some of what I already told you. Okay, I already drew this on the last slide. You have a chlorine. It's electron withdrawing. Now, we can draw resonance contributors for our chlorobenzene, where we do see electron density poured in the ring. And when we were talking about anisole, I said, well, you've got induction because oxygen is electron withdrawing, but then I said it can donate electrons through resonance. And when you have a battle between the two, you pick resonance. Well, I told you this is an exception, and induction has the greater effect. Okay, induction has the greater effect. And that's why halogens are deactivating. So you could write this down here. Induction, you could put here greater effect than resonance for this case only. Therefore, just put here deactivating. And that is why. But even though it's deactivating, I told you the electrophilic aromatic substitution reactions will occur at the ortho and para positions. Well, that you can guess has something to do with the sigma complex. And if you guessed that, you'd be 100% correct. Why? Same rationale that we saw with the nitro in a way, in that you end up with an extra resonance contributor when you do the nitration at the ortho or any kind of substitution at the ortho and para positions with a phenyl halide. So, whether you have bromobenzene, iodobenzene, chlorobenzene, or some derivative thereof. Let's take a look. So we have our nucleophilic attack from our chlorobenzene onto the nitronium ion. And if you look at the resonance contributors, we have the positive charge next to the chlorine. Well, what do we know? If you have some kind of resonance contributor where you have a pair of electrons next to a positive charge, you know that you can dump those electrons in there, can't you? And that is what would give us the last contributor right here. And we don't see that when we look at the meta attack. We have three beautiful resonance contributors to the sigma complex. However, none of them have the positive charge adjacent to the chlorine. And so again, with the para attack, we see the same thing. We have the positive charge here, here, and here. And here you go. There it is. That's the one that reveals that we have an extra resonance contributor that we have in the green box. And so to get it straight, again, if you have an electron donating group, it's going to be an activator. It activates the ring. What does activate mean? It just means it makes it more reactive than plain old benzene. Okay, more reactive. It's going to react faster. It's going to preferentially undergo electrophilic aromatic substitution at the ortho and para position. The only exception where we get more ortho than para product would be toluene. Then if we have an electron withdrawing group like a nitro, we'll see some other examples. If we have an electron withdrawing group, the substitution reaction will occur preferentially at the meta position. We discussed why that is. And then the exception are the halogens, which are deactivators. However, like a nitro group, however, substitution occurs at the ortho and para position. And again, the rationale for everything that I just summarized in the past 60 seconds or so is based off of the sigma complex. All right, and that's why this mechanism is so crucial. The nucleophilic attack to form a sigma complex, and for my students to be able to draw the resonance contributors to the sigma complex. Well, let's take a look at a summary of what would make a strong activator. Anything that's kind of got a lone pair just plunked right next to the carbon of the aromatic ring. Like we have this, so this would be phenol. This is a phenoxide. You can even pencil that in if you want. So this is phenol. This is called a phenoxide. It's just the conjugate base of phenol. And then, of course, this is aniline. And then we have some alkyl aniline and then some kind of dialkyl aniline derivative here. But you see that everything here, what do they all have in common? They have a pair of electrons to donate to make the ring, or to cause the ring to be nucleophilic, and that's why they're strong activators. Now, moderate activators also have a lone pair on an atom right next to the ring. However, those electrons on those atoms are also not only delocalized throughout the ring, but they're also delocalized outside of the ring. What does that mean? If you were to take this ester here, I could draw you a resonance contributor where I show the electron density being poured inside the ring, but I can also draw a resonance contributor where I show electron density being poured outside of the ring. Okay, and so if we have an oxygen next to a carbonyl or a nitrogen next to a carbonyl, so this is an ester, this is an amide. What do we have next after that? We have, this would be a, this one here would be a secondary amide. This one here would be a tertiary amide. And then you notice something that if you're very astute, and I know you all are, you might have been looking at this going like, WTF, man? Why isn't this up here? This doesn't have anywhere that these electrons can be delocalized outside of the ring. Organic chemistry is so annoying sometimes. Well, an alkoxy group kind of fits somewhere in between. So alkoxy is kind of somewhere in between strong and moderate. I love the way our book puts it. He says, an alkoxy group would be the strongest of the moderates and the weakest of the strong. Okay, so if you put it in the moderates, it would be the king of the castle, but if you put it in the strong activators, it would be the weakest one of all. So it's kind of in that gray area, if you will. I even wrote something down in my notes, which I can't read my own writing. Oh, it says, I even wrote the word kinda. It says kinda in between moderate and strong around the alkoxy. So that's, kind of one. Maybe we could put here strong / moderate. It's kind of in between the two. And then the weak activators, if you just have an alkyl group, whether it's a methyl, ethyl, isopropyl, terbutyl, whatever, acetbutyl, doesn't matter. If you just have a plain old alkyl group, well, we know that alkyl groups donate electron density through hyperconjugation, but that's not nearly as good or nearly as powerful as having electron density on your group that can be shown to be delocalized throughout the ring. Well, if you're wondering, what are some other deactivators besides the nitro? Let's take a look. So strong deactivators, nitro is the one that we see the most. If you take an aniline and you try substitute the nitrogen, so this would be called an anilinium. It's kind of like an anilinium type thing, so anilinium ion. The bottom line is that you've got a positive charge on the nitrogen, and so you could draw a resonance contributor where, no, actually you can't draw that because that would break the octet rule. But the bottom line is this thing is sucking electron density away like crazy because nitrogen is more electron negative than carbon, and it's got a positive charge on it. So you can imagine we could just draw the dipole like this. Like this is a mega dipole. So it just sucks electron density away from the ring like crazy. And then if you have some kind of trihalogenated, methyl group. So you take a methyl, you replace all the hydrogens with halogens, something like this. Like let's say you have tribromotoluene, like this. So CBr3, like that. All three of those halogens are withdrawing electron density away, and therefore it deactivates the ring. Okay. Again, the one that's going to come up most of the time in our class will be this one, and this one a little bit maybe. I don't remember if this is in any of the questions. I can't remember every question in the entire book. And then we have the moderate deactivators. I bet you can guess why all of these are moderate deactivators, because they all have a carbon with a double bond to oxygen, or a carbonyl, attached directly to the ring, or at least most of them do. So you could draw a resonance contributor that shows a positive charge inside the ring. So whether it's a ketone or an aldehyde, or a carboxylic acid, or if it's in, Mr. Dion couldn't see, I guess, whether it's an ester or a carboxylic acid or an amide. And we learned this one just last class, I think, the sulfonic acid, sulfonic acid. And you can see, same thing, you could draw resonance arrows like this, or a nitrile. This compound is called benzonitrile. We will learn the nomenclature of nitriles later on, but anyhow, you could draw this. But the bottom line is all of those are withdrawing electron density from the ring. Let's see, weak deactivators. Well, it's the halogens, chlorine, bromine, and iodine. Don't worry about fluorine. We'll talk about that later on in the course. But these are all weak deactivators. Why? Because they all have a dipole going in this direction. However, what separates these from the other deactivators is all the other deactivators were meta-directors, but you got to remember that the halides are the only deactivating groups that are ortho-para-directors, and we looked at why that is. It's because they have one extra contributor to the overall resonance hybrid, my friends. That is the reason why. Okay. Well, that covers all that. And here's the table. There it is, table 18.1. This is not a table you get to bring into the quiz or anything like that. All students have to become familiar with this. And you see it's kind of divided up into two main groups here. On the right-hand side, you've got the activators and the deactivators. You've got strong, medium, and weak, moderate, and strong. And we went over all those. And then it's also got it divided up into ortho-para directors, and we see that the halogens end up in there, even though they're deactivators, and everything else that's moderate and strong deactivator is going to activate the meta position over the other positions. And that's it, my friends. Well, I mean, that's not it, but there you go. You know, I was going to stop to ask you if you had any questions, but the best way to address, you know, do I understand or do I not understand what the heck is going on, is to try some practice. Question 18.16, for each of the following compounds, do something. Let's see. For each of these compounds, predict whether the ring is activated or deactivated. Then predict the strength of activation or deactivation. And finally, predict where the directing or where electrophilic aromatic substitution is going to occur. All right, so let's start out. We've got a nitro group. Well, we know that nitro groups are deactivators. We've looked at that. Would a nitro group go in the strong, moderate, or weak? Can anybody tell me that? Would nitro be strong? Exactly. And where did you get that from? So you have to refer to table 18.1 is where you're going to find that information, right, Caitlin? Absolutely. Great. So the nitro is a strong deactivator. And so where is substitution going to occur? It's going to occur at the meta position whenever we have any kind of deactivator, unless it's a halogen, which is a weak deactivator, which will direct to the ortho and para positions. So we'll highlight the two meta positions, and there you have it. The next one, we have a ketone, but the bottom line is we have our carbonyl attached directly to the aromatic ring. So could anybody describe that, what the effect would be? Is it strong, medium, weak? Is it activator or deactivator? And remember, there's no trick questions. Yeah, absolutely. Absolutely. It's a carbonyl. It's attached directly to the ring. We know it's deactivating because you could draw a resonance structure. You know, we could even take the time to do it, where we show that there's a positive charge, you know, delocalized throughout the ring. I'm just going to draw one contributor to the resonance hybrid, but I could draw this resonance contributor. Therefore, the carbonyl group, like Caitlin said, is a moderate deactivator, and therefore it's going to direct to the meta position. So let's highlight the meta positions, which are this position and this position. The next one, we got a bromine on there. I won't ask everybody about this one. The bromine, the halogens, we said it was a weak deactivator. Weak deactivator due to induction. It's not asking for that, but let's just pencil it in. But it is an ortho-para director. And that's because when you draw the sigma complex and you do substitution at the ortho or para positions, you get one extra resonance contributor because of the lone pairs on the halogen. And so, yeah, it's going to activate the ortho and para positions. So that would be these two and this one here. And the last one is something that we haven't really looked at. If you're wondering, what the heck is this? I've got a double bond, but notice we've got a double bond right next to the aromatic ring. And notice that there's a difference in electronegativity between a carbon and a nitrogen, right? This would be akin to saying, okay, well, you've got an aromatic ring. And what's the difference between this and if you had, you know, something like that, right? The bottom line is that either way, you can draw a resonance contributor like this. I'll put in my lone pair on the nitrogen, and then I'll make my double bond down here. So the bottom line is we can show a positive charge being delocalized throughout the ring. I'm going to erase this. Let's draw the resonance contributor here, just for fun. Oh yeah, it's a real hoot. So what's it going to look like? It's going to look like this, where we have a double bond here onto our nitrogen. which has 1, 2 lone pairs on it, a negative charge, and we have a positive charge over here. Therefore, this would be a moderate deactivator. So moderate, oops, I didn't draw my brackets. There we go. Moderate deactivator. And we said that a moderate deactivator is going to direct to the meta position. And let's highlight that meta position, which would be here. Oops, son of a gun, where's my green highlighter? Here we go, here and here. And just like that, my friends, we are good. Everybody with me on that? Go ahead.
Question. So I could see how you knew that that was a deactivator, but how did you know it was moderate deactivator?
Because if you go back to the table, so let's go back to the table. Anything that's a moderate deactivator always has a way to delocalize electrons away from the ring. And if you look at the nitro, it's just much more electron withdrawing because you've got 2 oxygens, which can hold that negative charge. So whenever you have a double bond directly attached to the ring, right, the double bond in the nitro is not directly on the ring. It's 1 bond away from the ring, so to speak. And so that's how I knew it was moderate. Does that make some sense?
Okay, yeah, that makes sense.
Yeah, good. All right. You know what's cool, Caitlin, is that later on when we look at SNAR, we look at how nitro groups, really come into their own in just like some really cool things that you can do with nitro groups and how they can be that reservoir for a negative charge. Okay, so that's enough of that one. Let's move on to multiple substituents. And, part of me wants to take a break and give you a break, but part of me knows that this information is fresh in your brain. And so I just want to run over this with you, not quickly. I don't want to rush over it, but I want to go over it with you, even though you might be tired, just to kind of get the ideas fleshed out. Because you're going to run into many situations in our book and in quizzes or exams, or if you're studying, let's say you want to be a veterinarian and you're studying the prep exams for that, you might run into this situation where they ask you about a question like, you want to do a bromination on an aromatic ring, but you've got 2 substituents. Okay, now so far we've only looked at the effect of 1 substituent. So what happens when you have more than 1 substituent? We'll check it out. It says here, the directing effects of all substituents on a ring have to be taken into account. You got to look at everything. Say, well, what effect will this have? What effect will that have? And in this molecule, we have a methyl group, which we know is an ortho pair director, and it's electron donating. It's an activator. And then we have a nitro group, which is meta directing, and it's a deactivator. But anyhow, it's that the directing effects of the methyl and the nitro guarantee that we're only going to get one product. Let's think about this very carefully. What are the ortho and para positions to the methyl? Let me use my highlighter. This is a para position. Nothing is going there, my friends, because there's already a nitro group in the way. So forget that. But these are the 2 ortho positions. Okay, well, we know that a nitro is a meta director. Where's the meta positions to the nitro? Here and here. So both of these groups are directing to the exact same place. So it's a no question asked. No, not a no-brainer. I shouldn't say that. I don't like that expression, but I think it's obvious, or rather obvious, that the bromination is going to be forced into the ortho position to the methyl group and the meta position to the nitro. Give me a thumbs up if that just makes sense. And if it doesn't, don't hesitate to ask me a question. Yeah, pretty cool, huh? But you can imagine, well, you're probably sitting there going, well, hold on, Mr. Dion. What if you have 2 things that are ortho para directors and then they're like meta to each other? Well, what do you do then? Hold on, we're going to get into that in a second. So here's another example. If groups direct to different carbons, who wins? Here's the answer. The stronger group will dominate the directing effects. Now, I know there's always somebody in the class, and I'm not pointing a finger at anybody, it doesn't matter. Like, this is a great question. There's always somebody who asks me, what if you give me 2 strong activators? Well, which one wins then? I'm never going to ask you that. I'm always going to put you in a situation where you can make that judgment call. You'll be able to say, well, I know that a hydroxyl is a strong ortho para director, and a methyl group, it's an ortho para director, but it's weak. So let's see. who's the winner? It's going to be the strong ortho para director. The para position is blocked, so we can forget about that. But these are the ortho positions to the stronger activator, and so our nitro group is going to go in there. So what I have highlighted here in this paragraph, that's the answer. The stronger group is the winner. And just remember, you have it on, it's going to be on my YouTube channel. Okay, I stated that I'm never going to put you in a situation where you can't figure it out. Are there situations beyond the scope of our course? Absolutely there are. Of course there are. But is that my job to ask you a bunch of things that we haven't covered? No. My job is to test you based on what we've covered in our class. So don't ever think, oh no, he's going to pull a fast one on me. No, that's not the point. Now, a couple rules that we have to go over when we're talking about multiple substituents. You ready? How many rules are there? I always forget. Sometimes I can't remember. There's 3 rules that we have to talk about. Oh, sorry. Sorry about that. It's my brother.